Hello and welcome everyone. Let's begin with a couple of announcements here. These are the announcements for class number 3 on Tuesday the 29th of August 2017. If you found this video, I guess that means you remembered that today's class meeting is presented online. So today, Tuesday the 29th of August, if you're watching this on the day that the lecture was originally scheduled, homework 2A is due. And so you can submit that assignment electronically on MU Online according to the normal process. Looking a bit further into the future, please take note that homework number 2B, with the problems that are listed there and also in the class schedule, that homework assignment is due on Tuesday, September 5th. Also will be an electronic submission. So please take note of those two assignment deadlines, and also the next class meeting that we're going to have for Thursday, August 31st. So that class is number 4, also going to be online, but we'll return to our normal in-class schedule on Tuesday, September 5th. So I will see your bright and smiling faces on that day. Today we're going to be covering two main topics. We're going to be discussing pressure and talking about its units, and then also the phenomenon of surface tension. Now, the majority of this lecture was previously recorded in a different semester, and so there may be some incidental references to dates and times that may not line up exactly, or there could be some interaction with a live classroom audience. So just to let you be aware that this is a lecture from last year, but the material is the same, the concepts are certainly the same, and I'll invite you to feel free to email me if you have any questions.
All right, so what kind of car is this? Oh man, don't you wish you had one of these cars? Wouldn't it be the best? I do too. I probably never will, at least not this one. This is the one that's like almost $100,000, right? It's not the cheap Model 3 that they're eventually going to be coming out with. The tire pressure is probably the most boring thing about the car, and that's what we're going to talk about today, is the tire pressure. Sorry. If you look up, in most cars, if you open the door, it's in the door jamb, you can look up what the tire is supposed to be inflated to. It's a strange place for them to mark that, but it's pretty consistent among vehicles. And on the Tesla, if you look it up, the tires are supposed to be pressurized to 45 psi. What's typical for other vehicles? 35, 32. My tires on my car are supposed to be 26 for whatever reason, really low. But these ones are 45. I guess probably for fuel economy. They say electric cars, people who do so-called hypermiling, where you're really trying to squeeze a lot of efficiency out of a car, you have very rigid tires because then there's less rolling resistance. And that's probably the case here. But this is how you measure tire pressure. It's the cheapest way. You know, you can buy these at Walmart for $1 or $2. So who can explain, or just guess, how does this instrument work? How does it tell you what's the pressure of the tire? It pushes the little thing out. There's probably some sort of a spring in there that provides resistance, and it only goes out so far as the pressure in the tire. But actually, the air that's surrounding this device has an effect on the reading that it gives. It's not just the tire pressure, but it's also the atmospheric pressure that affects the gauge reading. And to illustrate that point, consider another electric car. Okay? Which one would you rather drive? This one, really? That would be pretty cool, right? Rolling up to a stop sign in one of those? I don't think it's street legal. Only on the moon. All right? But it's got rubber tires. And if you measured the pressure of those tires on the moon, how would things be different? A vacuum. All right, I heard a really important key word. The moon doesn't have an atmosphere. And so, in the case of the Tesla on Earth, you're measuring that tire pressure relative to the air pressure that's pushing in on the tires. There isn't any surrounding air pressure pushing in on these moon vehicle tires. And so even if it was the same absolute pressure in both vehicles, the so-called gauge pressure reading would be different on Earth than it would be on the moon. So let's talk about these two ideas, absolute pressure versus gauge pressure. All right, so absolute pressure is when you're using a reference point of zero pressure, or the vacuum of space. So you're saying, let's measure the pressure, which the pressure is a concentration of gases, or in terms of what we've been discussing so far, pressure is directly related to how many molecules are in a given space. And so in vacuum, there are no molecules in a given space. And so you're measuring all of those readings against no molecules. So just as an illustration, the typical atmospheric pressure in Huntington is about 101 kPa, 14.7 psi with a little a on it. The a means absolute. My tires, on the other hand, if I fill up my tires relative to this absolute pressure, then I'd have to measure the pressure of the atmosphere, and then there's some additional pressure beyond the atmospheric, and so on an absolute basis, my tire pressure is 335 kPa. By contrast, the gauge pressure is when you're using some other datum point as your beginning reference for measuring. So you're saying, let's say atmosphere is 0, and measure everything beyond that 0 point. Okay, so if I was going to say, what's the gauge pressure in Huntington of the atmosphere? Well, by definition, it's 0, because gauge pressure means relative to atmospheric. So the atmospheric pressure relative to itself is 0. But my tire pressure is going to be some increment above that. And if I keep my tires at 34 psi, that translates to 234 kPa. So just another way of looking at it is with this diagram. We've got two lines against which to measure pressure. Vacuum is the lowest of the two. There's no such thing as a negative vacuum pressure. The atmospheric pressure is 101 kilopascals above vacuum pressure. So that means that there are some molecules floating around in this air right now, and so we do have some positive pressure in terms of absolute pressure for the atmosphere. But if we are measuring something like my tire pressure from this atmosphere line, it's shorter because the datum point is closer to my tire pressure. And so here I've got the two different pressure readings. I've got the gauge, which is 234 kPa, and the absolute pressure of my tires, 335 kPa. So the difference between the two is just the basis of measurement. It's where you're saying 0 is. Sometimes we say atmospheric pressure is 0, and sometimes we consider vacuum as 0. When we're doing gas law calculations, for example, it's common to use absolute pressures. For most of the rest of the course, we'll just go ahead and use atmospheric pressure as our starting point. And so we'll be using gauge pressures most of the time. I'll do my best to keep them straight as we go through examples and quiz problems and homework problems and so on. So are there questions? Yeah, go ahead.
So how much of a change in your tire pressure would there be if you went, say, from filling it up in the Rocky Mountains to dropping down to sea level?
That's a great question. That's a great question. I'm not sure, but we have some problems in coming up not in a couple of weeks where we look at what's called the dry adiabatic lapse rate, and that is the relationship between temperature, pressure, and elevation. So we'll do some calculations, but I don't want to say it's going to be a certain percentage because I'm not sure. We'll get to those calculations. It's a good point. We'll come back to it. All right, so let's refresh your memory of the gas law calculations that we did in class last time, and also make use of this new understanding that when we're talking about pressures, we need to differentiate between absolute and gauge pressures. So here's a gas law example where we've got a tank of oxygen, and by the way, we can look up an R value specific to oxygen that's here. And we know the volume of oxygen and the extent to which it's pressurized. The metal of the tank itself is 50 kilograms, and the temperature is 120 Celsius. And of course, red flag there, if our R value has units of Kelvin, that reminds us that we have a conversion that we need to do before we jump into the calculation. So what I'd like you to do is, in the similar way to when we were talking about the volume of a room and the mass of gas in that room, in this case, find the weight of the tank. And weight meaning units of newtons. What is the force that would be exerted by that tank on the floor, accounting for not only the weight of the tank, but also the amount of gas that's pressurized inside of it.
At this point in a live lecture, I would stop talking and let the students work independently or in pairs on the example problem. And so for this recorded video, I'll ask that you pause the recording, work through the example problem that's been provided, and then resume the video only when you've made your best effort to actually solve the problem, or if you get irretrievably stuck and need a little hint on how to continue.
All right, so on this one, I didn't go through all of the units double-checking backflips like we did in the gas law example from Thursday, you know, where I broke everything down to units of length, mass, and time. In this case, I did remind myself the R value units break down to meters squared per second squared per Kelvin, but then I left the pressure as newtons per meter squared just because I remembered that as long as you've got newtons per meter squared here, the R value there, and Kelvins there, what's coming out of that is kilograms per cubic meter. So you can find the density of the oxygen in the tank when it's pressurized to 7.6 megapascals. That's really high pressure. You know, that's quite a bit higher than atmospheric. So when you've got it pressurized that much, then the density is 74.9 kilograms per cubic meter. So then the overall mass of oxygen in the tank is just multiplying that density by the volume, and that's where the 187.24 kilograms comes from. But that's just the mass of the oxygen. We want to know the total mass, which includes the metal that the tank is made out of. So we have to add 50 to that, and then to get from kilograms into newtons, which is the measure of its weight, you simply multiply by G for that. All right. Any questions related to this example? Yes?
I did the exact same calculation,
74.01 for the density of oxygen? Anybody else get that same thing? There's every chance that my calculations have a mistake, but I've checked them a couple of times, so maybe afterwards we can go through it and see if there is a mistake in there. I think it's right. Did you also have a question? Yeah. Mm-hmm. Let's take a look at that after class. I don't want to get hung up on the units, but I do want to look at that. So let's come back to it. All right. So the second thing that we're going to be talking about today is surface tension. All right. So what is happening here? Well, it's a bug walking on water. How is this possible? What are the elements that make it possible for the bug to walk on water, whereas you or I wouldn't be able to do the same thing? Huh? How can the bug walk on water? Okay, well, surface tension still exists if I'm trying to walk on water. So how come I can't do it? Why not? It's really light. Okay, so element number one, that bug is lighter than I am. Okay, that's part of it, yeah? Okay, you say intermolecular forces. That's a really important part of surface tension. It's kind of the origin of surface tension, is the fact that the water molecules are attracted to other water molecules. Water's polar, so that's a big part of it.
Is it the way the bug equals the force of the surface?
It's something close to that. We will look at the equation for surface tension force. It's not just the weight of the bug, though. What do you notice about the legs of the bug? They're flat, big surface area. Yeah, what would happen, do you think, if instead of having its leg along the surface, what if it had the same length of the leg, but it was pointed downward? Yeah, it would be more pressure. It would pierce that surface tension. It almost looks like a membrane. From the deflection of the water that surrounds the leg, it kind of has the appearance of maybe some sort of like a plastic surface. You know, we know that it's not, that it's just this water being attracted to itself, but if you overcome that attractive force of the water, then that's what causes you and I to plunge through the water surface compared to the bug, which can just skim around on it. So it doesn't weigh very much. It's spreading out its weight. And what we could say from a kind of like a calculation basis is that the downward forces are less than the effects of surface tension. And we'll go over in a moment how to calculate those surface tension forces. So it's similar to how a paper clip can float on top of water. It's not that the paper clip has a density of less than water, which normally is required for something to float. It's just simply that the weight of that paper clip is distributed, and it can be supported by the surface tension because of the polar properties of water molecules being attracted to one another very strongly. Let's just watch a little video here.
All right, so here we see a lizard that's able to walk across the water. And if you think about how that's possible, it is a function of the surface tension of the fluid. And so the weight of the lizard acting downward is counterbalanced by some force that's supporting the lizard when we're talking about the forces in the vertical plane.
Let's do a cross-section of water. This is just a conceptual representation. This isn't to scale. This is just kind of an idea that explains why this membrane exists at the surface of the water. Let's begin by considering a water molecule that's submerged underneath the water surface. And so where is that water molecule expressing its attraction for other water molecules? Well, it can look to both sides. It can look down, above and below. So, you know, it's trying to have an attraction to other water molecules, and it can do that in a lot of different directions. In contrast to these water molecules at the top of the water where it interfaces with the air. These molecules have the same degree of attraction to other water molecules, but they can't be attracted to water molecules above them. They have that same force to express just with the ones that are to the sides and below it. And so the bond between these top water molecules is stronger than the bond of molecules to one another below the water surface, just because of the absence of water molecules above them. And so what that creates is the membrane. And different fluids have different surface tension constants. You can see that for room temperature water, the surface tension constant is 0.073 newtons per meter. And the units there are force per length. It varies as a function of temperature. The surface tension constant gets lower as the water is heated. And some liquids have remarkably high surface tension constant. Mercury, that one that is unusually dense, you know, it's 13.56 times of the density of water. It also has a really high surface tension, and it's just a pity that mercury is poisonous because it would be a lot of fun to play with because of its density and because of how it sticks together. It's too bad we can't, you know, throw it around the classroom to play with. Some of these have really low surface tensions. You can see that the surface tension of alcohol, for instance, is very low. And so we'll get a sense for that when we go to the lab and are taking a look at some of the fluid properties related to surface tension. Here's the equation of it. You can find out the magnitude of the surface tension force in terms of newtons by simply multiplying that surface tension constant, which is newtons per meter, by a length. But the question is, what length do we use? Let's go back to the picture of the bug. So the force of surface tension, the formula we were just looking at on the previous slide, F is sigma, that's the wrong word, sigma, multiplied by length. Okay, so the length is actually more than just 1 times this bug physical length. It's actually 2 because both sides of the leg contribute to the length. In other words, if we have a cross section of here's the bug's leg and here's the water that's being distorted by the leg's pressure on it, it's actually bending the water on both sides of the leg, and so the physical length is one thing, but the length that we use for calculations is double that in the case of the bug walking on water. Another place where the surface tension effect is manifest is in little glass tubes that can be dipped into water, and the water is drawn up into the tubes because of the attraction of the water with the glass that the tubes are made out of. Glass has a lot of silicon dioxide in it, SiO2, and water has an attraction to the SiO2, the oxygen component of silicon dioxide, in the same way that water is attracted to itself. And so what water tries to do when a glass tube is dipped into water is drawn up in the capillary tube in order to maximize contact with the inside surface area of that tube. And so it's because of the surface tension force that we see this capillary effect, and we'll observe that in lab as well. When we do problems like this, we first of all realize that the diameter of the tube has an effect on how high up the water can be drawn. And we'll go through a calculation that shows why that's the case. Another thing that's important is the contact angle. Sometimes it's called the wetting angle. In the case of water, we assume that the wetting angle is 0 degrees, but for other substances like mercury, if we're doing calculations, what that means is that the force isn't straight up in the case of other liquids. But in the case of water, we'll assume that water is drawn up into the tube, and so the surface tension force is, in essence, pulling up on this column of water and resisting the weight of the water, which is acting downward. Those come into equilibrium when the water rises to a certain height and then it stops rising. Equilibrium occurs very quickly. So here's a formula that describes what the surface tension force is going to be as a function of some length. Remember, what we saw before was sigma times L. So here, the length has been substituted by pi d. What does that tell you about what's the governing parameter for a circular glass tube? It's the circumference, which is a function of diameter. So the distance around the outside of the tube is how the water is being pulled up by the surface tension force. Since 0 is the wetting angle, cosine of 0 becomes 1. So in essence, the wetting angle aspect of water is neglected, and so the surface tension force is just a function of the surface tension constant and the circumference of the tube. So here's the question. How high will water go in a capillary tube like this? How do you find out what will be the height? And you do that by a force balance. Let me bring the lights up so it's a little bit easier to see the board. Okay, so here we have some water, and we dip a glass tube down into the water. As soon as we do that, the water, since it's attracted to the surface of that tube, the water is drawn up and it keeps rising until it stops, and it finally comes into equilibrium at a certain point. And that certain point is reached when the force due to surface tension is equal to the weight of the water, which is acting downward. And so if we do the sum of the forces in the vertical direction, what we could say is that the surface tension force minus the weight is equal to 0. All right, so we have a formula for the surface tension force. It's there on the screen. What about the weight of the water? What is the weight of water above the water line inside of that tube. Good. Yeah, so the weight of the water is just going to be the volume multiplied by the density. All right, so what's going to be the volume of the water? Well, we have to have the cross-sectional area. So the area is going to be pi d squared divided by 4. And then the length of it will just be delta H, right? So volume is going to be area times delta H. And that's the track you need to go on for this illustration. Let's say that we have a glass tube and the inner diameter is 1.6 millimeters. The water temperature is 20 degrees Celsius, and that gives us the surface tension constant that we're supposed to use, 0.073 newtons per meter. Also, the unit weight of water, oh, actually, I made a mistake. It's not just volume times density. It would be volume times density times g. In other words, the unit weight, because we want our weight to have units of newtons. And if we had just multiplied it by the density, then it would have units of kilograms. So we'll use gamma, which is the unit weight. So back to the idea of this temperature. 20 degrees Celsius is what gives us which of the temperature-dependent surface tension constants to use. This is the one for 20 degrees Celsius. But also, the unit weight of water at 20 degrees Celsius is a little bit different from 9810, which is what we typically use. At 20 degrees Celsius, it's 9790 newtons per meter cubed. And that's another one of those fluid properties that you can look up in the back of your book. Okay, so I'm going to pause the recording and ask you to work through this equilibrium force balance. Set the weight equal to the surface tension force and find out the unknown height that the water will rise to, delta H. It always is good. If you can draw a sketch, you should on a homework problem. Even if you've got a figure there in the book right in front of you, it's a good habit to draw a little sketch, because as you go through the process of drawing that, something like a light switch goes off in your brain, and suddenly it's kind of like you've created the problem by drawing it yourself. Even though it's not your problem, it's just somehow easier to visualize and kind of like, in a kinesthetic way, kind of like create the issue in your mind. So by this sloppy little sketch, what I'm showing is that the water is being drawn up by the force, the surface tension force. The weight of the water is down. We've got some diameter of the tube and an unknown height that the water is being drawn up inside the tube. So here are the physical constants we know about the water: the unit weight, surface tension constant, the diameter of the tube. We're using a contact angle of 0. And equilibrium means that the force is in balance with the weight. So the weight of the water can be calculated as the volume times the unit weight. And we know the volume is area times the height, and so I show the formula for the area. Surface tension, setting them equal, and okay. There's like a shortcut equation that's in your book that I hope you'll never use. I hope you'll always do it this way by finding the weight of water inside of the tube, because the shortcut equation only works for circular tubes, and there are other shapes besides circular. There can be square tubes or rectangular tubes and so on. So, and this one is a lot more instructive in terms of what's actually happening. You know, it emphasizes that through this process, it's an equilibrium that occurs. And so let me ask you this. What do you think would happen to the delta H if I made the glass tube smaller in diameter? It would go higher. Yeah, why would it go higher? Because let me play the devil's advocate here. If you make it a smaller glass tube, diameter, then the surface tension force is decreasing, because remember, surface tension force is a function of diameter, and if you make the diameter smaller, then the force is lower. The weight is also lower, right. It's a lot lower, because the weight is a function of diameter squared. And so when you make a small reduction in the diameter, you're going to have a small reduction in the surface tension force, but a pretty big reduction in the weight. So soil is kind of a case where the capillary effect is very important. And if you've taken a soil mechanics class before, are you in it this semester? No soil mechanics class yet? Well, in hydrology and soil mechanics both, you'll learn more about what you probably already know is there's something underground called the water table. And so here's the air, and beneath ground there's soil. And then if you go far enough down, there's actually water down there, where all of the soil voids are full of water. But there is some soil moisture even above the water table. The water table is where all of the soil voids are full of water. But these little connected soil grains, if there happens to be a collection of them small enough in diameter, interconnected soil voids, then water is drawn up above the water table, and so that roots from a tree don't have to go all the way down to the water table. They just have to make contact with what's known as the capillary zone because of the capillary effect.